This lecture, we're going to start looking at reactions of benzene. And so the kind of the name of the game with benzene reactions is electrophilic aromatic substitution. And that's abbreviated as EAS, electrophilic aromatic substitution. And these are reactions where benzene, a benzene, CH, is replaced, and I should highlight here a benzene CH bond. We don't replace the carbon, is replaced, it's the hydrogen, is replaced by a great electrophile. I'm going to label that as E+. Okay. So what this looks like is if we take benzene, I'm going to highlight one of the hydrogens. This is the one we're going to replace. Excuse me. And we're going to add that to E+, which is a terrific electrophile. What we're going to do is just swap out that hydrogen for the electrophile E. E has substituted the hydrogen atom. We get H+ as a byproduct. Now, the thing to note here is after the reactions occur, we're still aromatic, which is great because aromaticity provides stability to the molecule. Okay, so the driving force for this reaction is to sort of neutralize the electrophile E+, because for this to be a great electrophile, it's highly reactive. And if it's highly reactive, it's highly unstable. Okay. So let's go through some examples of electrophilic aromatic substitution reactions. We're going to stick with halogenation of benzene to start. Now you notice I call this halogenation of benzene, not dihalogenation of benzene. That was a reaction we did see with alkene. So I'm just going to recap here some things that we've been introduced to. So the first one is if you take just a run-of-the-mill alkene that's not in aromaticity, so I show that as cyclohexene. If we take that and we react that with Br2, we will form a trans dibromide, both enantiomers. I'll just depict one. Okay, so that's the product of the reaction for the dihalogenation of bromine. Now, if we try the exact same reaction on benzene, we don't see any reaction. So we don't see any reaction. I'm going to put the NR over the arrow. I'm going to draw, what a product could be. I mean, if you propose this, you would be thinking along the correct lines, treating that pi bond like any other pi bond. Sure, that's a good guess, but it turns out that doesn't happen. Okay, no reaction in this case. Br2 does not engage the benzene on its own. Now, if you recall, I'm saying we've seen this before. If you recall, when Kekulé did some experiments on benzene when he was trying to deduce the structure, he would take benzene and react it with Cl2 with lots of heat, and he would, for the most part, get benzene plus some trace monochlorinated product, but he wouldn't get a ton. Okay, so this is mostly no reaction. And under some forcing conditions, he would see just a subtle reaction, but it would only be the monohalogenated product. He wouldn't see any of this trans dichlorinated product. So there's a trace amount of monohalogenated product. Now, since that time, we've been able to figure out how to get this reaction to go and proceed more efficiently. We just needed to add a catalyst. So if we add a catalyst to this reaction, we can get it to go. And again, the reaction is actually different than that of a typical alkene reaction. What we would do is we would add Cl2 or Br2 or I2 with a catalyst and form the monohalogenated product. Okay, so a typical catalyst that you could use is FeBr3. FeBr3. Okay, so Fe, it turns out in this case, is sort of like, it kind of behaves like boron or aluminum, it turns out. It's mostly just a Lewis acid. Okay, so how this works is that the FeBr3 actually reacts with and activates the dihalide. So it reacts with and activates the dihalide. That's an important note to capture here because it allows us to envision what's sort of going on. So what I'm saying is that the FeBr3 first reacts with X2 to make a super electrophile with X. Okay, it's sort of like an X plus, which could be Br plus, Cl plus, I plus, or whatever. Okay, now, if you recall from our understanding of Br2, Cl2, and I2, they are kind of already like Br plus, Cl plus, and I plus. It's just a halogen attached to a good leaving group. So it's kind of that way. But there's no like dipole because they have the same electronegativity. So what we do is we use the catalyst to activate. Now here's what the arrows look like in terms of the mechanism. So this would be the mechanism for activation. Okay, so what we do is if we take Br2, for example, I'm going to draw it this way. Now Br2's got several lone pairs around the bromine atoms to consider. We'll just pick one. Now the Fe, I like to think about it as sort of like a group 3 element. It's not, but this is sort of a healthy way of thinking about how the reaction proceeds. We have an open coordination sphere where the lone pair on the bromine atom can engage. So this is kind of like Lewis base adding to a Lewis acid. Now, if we do it this way, what we get is something that looks like this. Now, it's not super precise, but I like to show the Fe as having a negative charge. And the reason why is it shows that the complex is overall neutral and the bromine has a now formal positive charge. Now it's the central bromine that has a positive charge. If you look at it, it's a group 6 element, used one of its lone pair of electrons to attack, group 7 element. So it's 7 minus 4 minus 2 bonds, that's equal to plus 1. So it's the formal charge on bromine. Okay, so now what we can do with this complex is actually add a nucleophile to the complex. The nucleophile is going to add to a bromine atom so as to neutralize the positive charge. So we have a positive charge at the central bromine. We're actually going to add the nucleophile to the bromine that's attached to that positively charged element. So the negative charge isn't going to go out here, because think about it, once it goes there, what's it going to do? Like just add and sit there? Bromine's already got an octet at this point. We have some d orbitals available to us, but being a main group element, not a transition element, it's probably not super thrilled about soaking up more electrons. Instead, what we could do is take the negative charge and attack the Br next to that positive charge and push this sigma bond of electrons into the Br with a plus. That's going to have a nucleophile with a bromine attached to, and I should have this negative charge here, attached to a now neutral bromine with an iron and 4 bromines, excuse me. Okay, now at this point we've made product after we add the bromine, but the Br is not done yet. It would rather be neutral, so it's just going to let a Br walk away as Br minus. Then we get our catalyst regenerated in effect after the Br minus walks away. So the catalyst is regenerated. Okay, that's an important part of a catalytic process, is that you consume the catalyst and it then becomes a product for the overall reaction. Notice that also the Br minus is a product for the reaction. It's as if the nucleophile sort of added to the Br2, adding it to a Br and then pushing electrons on the Br to give a Br minus. So this looks like the nuc minus just added to Br2, right? Because I say that Br is a good leaving group, so we could just have the nucleophile add and push electrons off to make our nucleophile with our bromine. We've actually done reactions like this, and our Br minus is lost. Now, it looks like that, but it's catalyzed. So when catalyzed, weaker or poorer nucleophiles can add to the Br center. So we can have less good nucleophiles doing adding to our Br2 when we have, and I'll write the 2 here, when we have the catalyst present, because we've activated it, we've introduced that positive charge. That allows for a weaker nucleophile to add to the Br2. Now, what kind of weak nucleophile would we want to add? That weaker nucleophile could be benzene. Benzene, because benzene's not a great nucleophile. It's a happy aromatic molecule. So if you tell it it can undergo a reaction, it's going to be like, I'm already aromatic. And I'm already quite stable. We talked about how stable it was in the last lecture. So why are we trying to do a reaction if we're a happy organic molecule already? Well, it turns out that when that catalyst is present, the electrophile, which is our Br2, becomes really unhappy and really willing to get neutralized by just about anything. Okay. So benzene is, in general, not a good nucleophile, but it will react with super electrophiles. And just so happens one of those examples is our complex Br, Br, Fe, Br, negative, positive. Okay. What we're going to do a lot in this module is we're going to look at interesting reactions of benzene under with different super electrophiles. So in each case, we're going to have a different electrophile, but the overall reaction involving benzene is going to be the same. So the general electrophilic aromatic substitution reaction looks like this. We take benzene. Now benzene is going to be our nucleophile. It's hard to see where that nucleophile is, but it's just one of the pi bonds. Okay, so we're going to take that nucleophile and we're going to add it to an electrophile. And the arrows are going to look like this. We're going to steal one of the pi bonds to make a new sigma bond with our electrophile. So the other two pi bonds are going to remain the same. We're going to form a bond with the electrophile. And when I form a bond with an electrophile, I also like to get in the habit of drawing the H that's on the carbon that accepted the electrophile. That's going to be next door to a positive charge. That positive charge is kind of the hole where we lost the electrons. So we have this intermediate structure. Now that intermediate is going to lose the H on the carbon that accepted the electrophile. Now that's the H we want to lose anyway. That's the H that gets substituted. When we do that, we get back to a neutral structure and our electrophile is now bonded to the benzene. So this is our general reaction. We have our super electrophile. I just like to make note of a super electrophile. That's sort of my term, but it helps me because it reminds me that, hey, you know, we're going to see some different types of things, all sorts of different types of electrophiles adding, but it's not just every electrophile. It has to be a pretty pumped up, ready to go electrophile. Okay. Now this, I'll highlight this right here. This is our sigma complex. That's an intermediate in the electrophilic aromatic substitution process. It might not be the only intermediate depending on the super electrophile that we use, but it's the general intermediate that we see in every case. Now let's put this together for the bromination of benzene. Okay, so what we do is we take benzene and we react it with Br2 in the presence of FeBr3. And we do this exact reaction, but we have a super electrophile that allows us to introduce bromine. Now the mechanism for this is, well, actually, let's first make our super electrophile. Unless the super electrophile is already generated, that's the first part of the mechanism in every case. So we're going to have Br2 add to FeBr3. FeBr3 is just sort of going to act like an electron hole to take on any lone pair of the Br2. It can be on the left side or the right side, whatever. Just one of the lone pairs of electrons on Br2 gets taken up to give us a complex where this serves as a super electrophile. I put the positive charge at the central bromine because that's where it's at, but that's not the super electrophile. That's not the electrophilic part. Rather, it's the atom shown here. This is our electrophile. Okay, so we can add a nucleophile to that bromine now that's a lot weaker than it would be otherwise. So bromine is our nucleophile of choice in this unit. Okay, so we're going to take a pi bond and add, oh, I got negative charge. Shoot, I'm sorry, positive, negative. Okay, so the pi bond of benzene is going to add to the Br and push the electrons from that bromine, of the bromine-bromine bond into the bromine with a positive charge. That's going to give rise to two things. One's going to be our cationic intermediate where we have a bromine added and a positive charge at the carbon that lost the double bond. I'm going to always make it a habit because it's going to make my life so much easier to draw the hydrogen on the carbon that accepted the bromine. This is the hydrogen that we lose. Okay, I don't draw the hydrogen on the positive charge. There is a hydrogen there, but it's not helpful to consider at this point. I mean, you could draw it, but it's not one to be lost, and that confuses people sometimes. So it's always on the carbon that accepts the electrophile. Additionally, I'm going to have Br FeBr, Br, Br. And at this point, I can be done with the FeBr4. I mean, I know that breaks down. It loses Br minus to regenerate my catalyst. In terms of proposing a mechanism for the formation of product, I don't necessarily have to consider it. So, I mean, I will. It's a good habit to get into. And we could lose any of these bromine atoms. Just another example of how the catalyst that goes in has to be a product for the reaction, but it's certainly consumed. So my point is, any of those bromine atoms now are all symmetric. We could lose any of those bromine atoms. And so in theory, the three bromines that you started with in your catalyst aren't the three bromines that you get out at the end. And the catalyst was consumed, but it's still a catalyst. It's accelerating a reaction that wouldn't occur. And the product, or the catalytically active species, is regenerated. It's a product at the end of the reaction. Okay, anyway. Somebody might say, well, it's the iron that does everything. It's like, come on, man. I'm just trying to help you out. Okay, so anyway, at this point, we can lose the hydrogen atom that's attached to the carbon that just accepted a bromine atom. That's going to regenerate aromaticity, which makes us all very happy because we're aromatic again. And it's going to give us a product with a Br. This is driven by the fact that we used an electrophile that was more unstable than the H+. You could say this, the side or the byproduct of this reaction is HBr. If you let the Br minus that's generated from the catalyst adduct with the H+, but that's a strong acid anyway. All I care about is formation of the product and having some idea that the catalyst turned over and got back to normal. Okay, so I'm just going to remind ourselves that the catalyst is regenerated because if you go into the lab and you put this compound into a flask, it will go to very quickly to HBr plus FeBr3, and that's our catalyst. So I know I was just emphasizing that, but let me just write it down. Okay, so we can do the same thing with some other halogen atoms. We can do this with iodine. And some folks might want a different catalyst, but for our purposes, we can use FeBr3. It's easy to get access to. That's going to give us an iodide compound plus Hi plus FeBr3. Okay. Now with chlorine, sometimes the elements get kind of swapped around and it's hard to know what you're putting into the reaction, and FeCl3 isn't as good of a catalyst. So you're going to change the catalyst if you want to do chlorination. So chlorination of benzene requires a different catalyst. And that catalyst is AlCl3, which is aluminum trichloride. I've used this stuff before, it works just fine. And there's other things too. Aluminum trichloride is a good one for us to focus on. It'll be the one that we use for our chlorination reactions or things involving chlorinated electrophiles. Okay, so here's what the reaction looks like. We're going to take our benzene and we're going to react it with Cl2 in the presence of AlCl3 to give us a chlorinated benzene. Now the mechanism of this is going to look very similar to the bromination mechanism. We're just going to have a different superelectrophile, but even the superelectrophile is going to look like the exact same except with some different letters. So let's go through the mechanism. The first step in an electrophilic aromatic substitution reaction is always to generate the electrophile. So I'll just make note of that here to remind myself that the first place I should go in this multi-step mechanism is to generate the superelectrophile. So I'm going to consider chlorine dichloride by showing the sigma bond between the two chlorine atoms and just depicting one of the Lewis dot lone pairs on the Lewis dot structure. Okay, now it's going to see aluminum. Now aluminum is a main group element, so we can think about it in terms of the rules we use for carbon, nitrogen, oxygen, that sort of thing. And the halides, where it's a group 3 element that desperately wants 8 electrons as an octet. So it can get those when it reacts with dichloride. Here's the issue though. Aluminum being a group 3 element, once aluminum and boron for that matter have their octet, they're negatively charged, negative formal charge, right? If you have a group 3 element and you subtract 4 from that for the number of bonds, subtract 0 from that, which is the number of lone pair electrons, 3 minus 4 minus 0, that's -1. So chlorine and bromine, or chlorine and, aluminum and boron are super weird elements because as soon as they achieve an octet, they're negatively charged. That's a good thing to hold on to. So we're negative here. Additionally, the chlorine is now positive. If you look at this, this is our super electrophile for the chlorination reaction. It looks the exact same as the Fe-Br3, except we've substituted the letters, we've replaced the iron center with aluminum. And because we're doing chlorination, we have chlorines everywhere instead of bromines so as to not mix things up a little bit. Okay, so this is our super electrophile. So now we can make our sigma complex by having benzene react with our super electrophile. We're going to use the pi bonds on benzene to attack the outermost chlorine atom, not the one that's positively charged, but that'll allow us to push electrons into the one that's positively charged to give rise to our cation intermediate. We have a chlorine atom attached. Now to make it helpful for me, I'm going to draw the hydrogen atom onto the carbon atom that accepted the chlorine. That's going to remind me which one is lost when we regenerate aromaticity. So we lose the H plus to give us our final product. Now that H plus AlCl4 is going to break down to form HCl and aluminum trichloride. Aluminum trichloride, that's our catalyst. Our catalyst has been regenerated. Okay, so we've looked at 3 halogenation reactions. Ones where we're introducing chlorine, bromine, iodine. We wouldn't do the same thing with fluorine, so don't worry about it. But these are our 3 halogenation reactions, and they are nice starters for us to look at electrophilic aromatic substitution reactions. But introducing halogen is just, one type of bond that we can make. We're definitely more interested maybe in making carbon-carbon bonds, especially from benzene. So in the next lecture, we'll look at that. We'll look at reactions where that are like these, where we generate carbon-carbon bonds. Okay, so until then, see you next time.